Okay, let us continue the third part of today's course. Okay, let us see this page. Okay, when these conditions hold, the channel matrix is denoted by HW. Okay. This nomenclature is used extensively in the MIMO literature, so we also adopt it in this course. Okay, the Chinese meaning of this word, nomenclature is 术语. Okay, so this nomenclature means HW. Okay, next let us go to section 3.9.2, capacity of an HW channel for large N. Okay, although it is normally not possible to obtain a closed form expression for the capacity of a MIMO system in randomly varying channels, there are certain cases where it is possible. One such example is when there are equal numbers of transmit and receive antennas, and the number of antennas is large. Okay, under that condition, it is possible to use the following theorem. Excuse me. Okay, theorem 3.1. For an n by n MIMO system where h is equal to hw, limit n approaches infinity, hw times hw Hermitian approaches n times in, where in is the n by n identity matrix. One of the implications of this theorem is that when n is large, the eigenvalues of hw times hw Hermitian are equal to n. Okay, this is because this matrix is a diagonal matrix, and the diagonal elements of this matrix are all equal to n. Okay, n, on the diagonal. And it is very easy to prove that the eigenvalues of this matrix are all equal to n. Okay, and it is left to you as an exercise. Okay, because you should be able to prove it after you take the course linear algebra. Okay, and the rank R is equal to n. Okay, it is more easy. Okay, it is easier. Okay, because it is a diagonal matrix. Okay, and each diagonal element is equal to n. Okay, so according to the rank, according to the definition of the rank of a matrix, the rank R of this matrix is equal to n. Okay, so it follows from equation 3.11. Okay, let us go to equation 3.11. Okay, we can see that in equation 3.11. Oh, sorry. Okay, the capacity is equal to summation I is equal to 1 to R log 2 of 1 plus rho over nt times lambda I. Okay. Excuse me. Okay, let us go back to this page. Okay, and now because nt is equal to n, Okay, because it is an n by n MIMO system, so nt is equal to n. So this term is nt originally, can be replaced by n. Okay, and we know that lambda I is equal to n. Okay, here. Okay, so we can replace lambda I by n. And very good, this n and this n can be cancelled. So we have each term is equal to log 2 1 plus rho, and r is also equal to n. So this equation equals to n times log 2 1 plus rho. Okay, this shows that when the number of antennas becomes large for an n by n MIMO system, the capacity becomes deterministic. Okay, because the capacity is equal to n. N is number of the transmit antennas or receive antennas. So n can be treated as a constant. Okay, times log 2 1 plus rho. Okay, and you can also treat rho as a constant. Okay, so C is deterministic. Okay, second, the capacity increases linearly with n. Okay, we can see that capacity C is equal to n times log 2 1 plus rho. Okay, so the capacity C increases linearly with n. Excuse me. Okay, next let us go to section 3.9.3, ergodic capacity. Okay, since the capacity C of a MIMO system is a function of H if H is random, so is C. Therefore, when the channel varies randomly, C is a random variable that can be characterized in terms of all the various statistics that are applicable to any random variable. The simplest statistic is the mean of the capacity. Okay, in MIMO and information theory literature, the mean value of the capacity is called the ergodic capacity. Although a closed form expression for the ergodic capacity of a MIMO system in Rayleigh fading has been derived, because of its complexity, we have chosen to generate results using computer simulations instead. Excuse me. Okay, figures 3.6 to 3.8. Okay, let us see figures 3.6 to 3.8. Okay, this is figure 3.6, which is the ergodic capacity of an 1 by nr SIMO system in Rayleigh fading. Okay, in this figure we can see that the x-axis is nr, okay, from 1 to 10, and the y-axis is the channel capacity from 0 to 14 bits per second per hertz. Okay, and there are 4 curves in this figure. Okay, the first curve is the line with the triangular marker. Okay, this curve, where SNR is equal to 0 dB. Okay, and the second curve is the line with the triangular marker upside down. Okay, this curve, Okay, and where SNR is equal to 10 dB. And the third curve is the line with the square marker. Okay, this curve where SNR is equal to 20 dB. Okay, and the first curve is the line only. Okay, this line where SNR is equal to 30 dB. Okay, we can see that when NR increases, the channel capacity also increases for all SNR values. Okay, and when SNR increases, okay, the channel capacity also increases. Okay, and in figure 3.7, this is the ergodic capacity of an NT/1 meso system in Rayleigh fading. Excuse me. We can see that, okay, in the x-axis, it is NT from 1 to 10. And in y-axis, it is channel capacity from 0 to 11. Okay, and there are also 4 curves in this figure, and the legend is the same as the previous figure. Okay, so in this figure we can observe that when NT increases, the channel capacity also increases. Okay, when SNR increases, the channel capacity also increases. Okay, and finally in figure 3.8, it is the ergodic capacity of an N/N MIMO system in Rayleigh fading. Okay, in the x-axis, it is NT, which is equal to NR, which is equal to N, okay, from 1 to 10. And in y-axis, it is the channel capacity in bits per second per hertz. Excuse me. Okay, and there are also 4 curves in this figure, and the legend is the same as the previous two figures. Okay, when N increases, okay, we can see that channel capacity also increases, and in a linear way. Okay, and when SNR increases, the channel capacity also increases. Okay, let us go back to page 181. So figures 3.6 to 3.8 show the ergodic capacity when H is equal to HW. Okay, is plotted versus the number of antennas for different signal to noise ratio values. Excuse me. Okay, for SIMO, MISO, and N/N MIMO antenna configurations, respectively. Okay, these results show that the behavior of the ergodic capacity is similar to the results for a deterministic channel. Okay, the results in figures 3.6 and 3.7 show similar dependence. Okay, we can see that as the number of NR or NT increases, okay, the channel capacity also increases, and the curve looks like the curves look like a log curve. Okay, so we say show similar dependence. Okay, in addition, figure 3.8 shows that the ergodic capacity increases linearly with the number of antennas for an n by n configuration. Okay, let us see figure 3.8. Okay, so in figure 3.8, the ergodic capacity, okay, or channel capacity increases linearly with the value of n. Excuse me, which is also observed to occur in equation 3.16 for a deterministic n by n full range channel. Okay, let us go to equation 3.16. Okay, in equation 3.16, the equation number is wrong. Okay, let me fix the problem. Okay, in equation 3.16, okay, we can see that the capacity is equal to n times log 2, 1 plus rho times zeta over n squared. Okay, where zeta is defined as, okay, let us see. Zeta is defined as the summation of all the eigenvalues of the matrix H times H Hermitian. Okay, so we can see that here capacity also increases with n linearly. Okay, let us go back to page 184. Oh, sorry, the next page. Okay, the next page. Okay, next, let us see section 3.9.4, outage capacity. Excuse me. Another common measure of the capacity of a MIMO channel is the outage capacity. The outage capacity is based on the cumulative distribution of C as illustrated in figure 3.9. Okay, let us see figure 3.9. Okay, figure 3.9 shows a generic cumulative distribution function of the capacity with an illustration of how the outage capacity is defined. Okay, in this figure we can see that the x-axis is C, okay, the capacity, and the y-axis is the probability of C, okay, being smaller than or equal to the abscissa, okay, where the word abscissa means the value of the capacity C, okay. So we can see that this is a CDF, okay, cumulative distribution function of the capacity C, okay, and it is a non-decreasing function of C, okay. And how do we define C out Q? Okay, C out Q is defined as, okay, the probability of the capacity is smaller than or equal to C out Q is equal to Q. Okay, so this value is Q, and Q you can draw a horizontal dashed line, and when it intersect with the CDF and the point, we also then we draw a vertical line and toward the C-axis, and the value of this intersection point is C out Q. Okay. So okay, this is figure 3.9. Okay, we define the outage capacity as follows. Definition: the Q% outage capacity, C out Q, is defined as the data capacity that is guaranteed 1 minus Q times 100% of channel realizations. Okay, I think this sentence is not easily to understand. Okay, so we can see the equation. Okay, that is the probability of C being smaller than or equal to C out Q is equal to Q. Okay, so I think that this equation is much easier to be understood. Okay, figures 3.10 and 3.11. Okay, let us see figure 3.10 first. Okay, in figure 3.10, it is the 1% outage capacity for an N by N MIMO system. Excuse me. Okay, and the x-axis is NT, which is equal to NR, and which is equal to N, okay, from 1 to 10. And the y-axis is the channel capacity from 0 to 90 bits per second per hertz. Okay, and we can see that there are 4 curves in this figure, and the legend is the same as that in figures 3.6 to 3.8. So we can see that as n increases, the channel capacity also increases, okay, in a linear manner. And when SNR increases, okay, from the bottom curve to the top curve, the channel capacity also increases. Okay, next let us see figure 3.11. It is the 10% outage capacity for an N by N MIMO system. Okay, we can see that this figure is very similar to the previous figure. Okay. So figures 3.10 and 3.11 show the 1% and 10% outage capacity plotted versus the number of antennas for an N by N MIMO system. Excuse me. These results show that outage capacity, like ergodic capacity, increases linearly with the number of antennas. Okay, so you can see that the curves in this figure and this figure are linear. Okay, a comparison of these plots with figure 3.8. Okay, let us see figure 3.8. Okay, figure 3.8 is this figure. Okay, we have seen this figure about several minutes ago. Okay, let us go back to this page. Okay, shows that C out 1 and C out 10 are less than the ergodic capacity as expected. Okay, for example, at rho is equal to 10 dB, C out 1 is approximately 24 bits per second per hertz. Okay, let us see the figure for C out 1. Okay, for C out 1, when rho is equal to 10 dB, that is rho is equal to 10 dB. Here, Okay, excuse me. And when n is equal to 10, we can see that the channel capacity is approximately, okay, it is 25 minutes. See you next time. Goodbye.